Okay, so we're going to move on to the next topic, which actually includes what we just talked about in intermolecular interactions and how they actually apply to the big world, kind of, and how we observe them and their behavior and the like. And we saw a little bit of that when we looked at phase diagrams and heating curves and solubility as well. And we're going to expand on that. There's going to be two PowerPoints here. This is chapter 12 of your book. The book is a good resource for this. The slides are basically most slides are taken from the book, and that's what you'll notice throughout this material is that the book is useful for the material here. I will be using examples uh, from the book as we go along. There will be more math involved, and the book will have more examples to do so. And I'll be assigning problems out of the book to have you practice so that you can become proficient in understanding what we are talking about. Okay, so let's move forward with mixtures at the molecular level, properties of solutions, okay, part one. So let's talk about solutions. And let's slide through them, okay, and see what this slide has to say, okay. So solutions, homogeneous mixtures, okay, so they're all the way, when you look at them, they look all the same. Like if you had a bottle of Coke, you would see that it's the same uniform composition all the way through. And so a solution is composed of a solvent and a solute. And a solvent is basically the room, and it is the most abundant of the mixture. It is the dissolver. In our case, usually it will be water. And then you'll have solute or solutes, okay, and they'll be less abundant, or the other components of the mixture. And they are the things that are dissolved, or a dissolvee. So like salt water, the solvent would be water, and the solute would be salt. Again, since it's a mixture, when you mix the solvent to solute together, their individual chemical properties don't change. Water is still water, and the solute is still the associated solute. And so it talked about lactate Ringer solution. This is kind of interesting. It's used. Lactate Ringer solution is used in hospitals to help restore your electrolytes. And there was kind of interesting thing was, I don't know if they have these right now still, but a couple years ago I read that there's these there would be these places, maybe in big cities, that after you may have had a real big night of drinking and got sick and dehydrated, you could go to these places and you could actually be hooked up to a lactate Ringer solution, and this was supposed to help you get over your hangover. Whether it did or not, I don't know, but it's interesting. They use this mostly in hospitals where you actually need to take care of this. And here's just the ingredients. So you have sodium chloride, potassium chloride, calcium chloride, and this is lactate. And really what it does is all of these, the main component is the positive ion, okay? Okay, and so this helps restore your electrolyte balance. Okay, why do solutions form? There are two driving forces behind forming a solution. Disorder and randomization and intermolecular forces. Whether or not a solution forms depended on opposing forces. And thermodynamic chapter, which I don't know what chapter it is. It's on entropy and thermodynamics. So let's see, look it up. Chapter 18. We'll define more precisely. All right. So let's look at mixing, and it's spontaneous mixing, which just happens when you mix two components together. And the best case is to look at gases, because gases, their movement is random, and what we're also assuming there's no attraction between the particles. And so when you mix two gases together, there isn't this molecular urge for the particles to come together in any kind of particular fashion. So what they end up doing is mixing perfectly as anything could mix, and that means they do it spontaneously. And they have it, and it's interesting is how fast it happens. And so gases are the best, at least ideal gases are the best way to look at pure mixing. Due to random motion of the particles, they mix without any work on the outside or inside even, and never separate spontaneous. So there's no reason for that. They could separate spontaneous, right? That's bad things. We'll find out, and maybe we'll explain it, but when we talk about entropy, most of the time the particles will separate 100%. Well, not 100%. They'll separate really high percentage of they will be mixed diffusely. And here's a case where you have a box separation, pull it apart, and then they'll eventually, depending on temperature, and pressure, and they will, and the volume, and it's how well they will mix spontaneously in no particular order. Okay. So key thing here, which we will get into when we get to entropy, the system goes from being ordered two separate sets of particles to being completely disordered. And we'll learn, and when we talk about entropy, is nature always moves to becoming more disordered. And that's a big thing. It has this chapter. I mean, this part of chemistry. Right, and then intermolecular forces. We've talked about this. So attractive forces between molecules and pure substances, solvents and solutes. Okay, now what we're going to look at is, so in the last chapter we look at like water. Why does water interact with itself? And we talked a little bit about other polar molecules interacting with polar molecules and nonpolar with nonpolar, but we're going to get talking about that more now. Especially how do mixtures form. One of the things is that when you put them together, there's this random mixing where they all move the particles around, and that's what gases do. Now, and gases don't have intermolecular forces. But now what we do is when we look at liquids, which most of the solutions that we're going to talk about, is that there's interaction between a solvent and a solute. And these are intermolecular interactions. Okay, all right. So strength of intermolecular attractive forces in a mixture compared to the pure substance will indicate if a mixture can form or substance remains separate. So one thing is that one of the reasons why oil and water doesn't mix is not because oil and water don't like each other. It's just that water has a lot stronger interactions towards itself than the oil. And because of that, it pushes the oil away because the water particles interact. So but if you take a substance that water can like, that has similar properties that are polar or has partial ion or ionic, then then it will mix and not separate. Okay, so let's see formation solutions depending on intermolecular forces. When mixed, a solution to form, the solvent to solute attraction must be similar to the attraction between the solute alone and the solvent alone. So again, if you put salt in the water, the water's got to interact as well as with the salt as the salt with its own self. If it doesn't, like I just said with oil and water, then you'll get little to no mixing. Okay. All right, now actually, so let's look at actually kind of the dynamics of what we think happens when you mix a solute in a solvent to make a solution. The first thing that actually happens is that the solute has to come into the room and make itself present, okay, so that it can be either liked or disliked. Okay. Sorry about that. Phone's ringing. And it's just some solicitors, I'm sure. Okay, so when you put a solute in a solute, first of all, they have to mix. And so for them to mix, what has to happen, first of all, is the interactions of solute. You put the salt into the water, the salt has to break apart, okay? And to do that requires energy because, like sodium chloride, there's a natural attraction between the positive and negative ion. And to break that, you need to add energy, okay? The other thing is also the water molecules have to be broken apart as well because they also are being disrupted. So the way you kind of think about it is that, let's say you have, I think of a giant party, you have 1,000 people that like each other, that's like the water molecules. And then you drop 10 people in that are, 10 couples, and they come in, we got to make room for them, all right? And what you have to do is you have to break everybody apart a little bit and see how they mingle. Okay, now and then what happens is you'll see if there's attractions where they can spread out, okay, and mix. Like when separated solute and solvent are mixed to make a solution, so first of all, they break apart individually, and then if there's interactions that could happen, like dipole or ion dipole, there's and so sodium Na plus with the negative dipole of water, there's energy released, okay, because they have come together, right? Right, and this happens. Okay, now if there's a net release of energy, so there's two parts here. One is the breaking of the interactions of the individual types of things, and that's endothermic. Okay, so you have to add energy. Okay, and then the making of interactions in the solution. Okay, if that releases energy, and then if you add these two up together and to make a solution, if you add these two together, if this term outweighs this term, you'll have a solution. So overall, if the energy goes down, okay, then you have a solution. Now there's some caveats there we have to take into account, especially when we get into talk about entropy, because that's not always the case. There's sometimes in the big scheme of things. So we would think that this would be an exothermic reaction where it gives off heat. There are some times when we make a solution where it's actually endothermic as an endothermic reaction, and it still forms a solid. And the reason for that is you have to take in not just the enthalpy change of this, you have to take in something called entropy, which we're going to be talking about when we get to thermodynamics. But for now, when these two things, we're just going to be looking at it as most of these as exothermic. Okay, miscible liquids. Miscible liquids are liquids that dissolve in each other and they form a solution. For instance, if you take ethanol, okay, ethanol is the main ingredient. A lot of people don't know what ethanol is, where you find it. Ethanol, whenever I ask my students, where have you heard ethanol? And they'll go, oh, that's what's in gasoline. I mean, they use it for gasoline substitute, and they make it from corn. Ethanol is actually found more in alcoholic drinks than anything has to do with gas and all that. Ethanol is the alcohol of alcohol. Okay, so but it also can be used as a fuel. It's two different chemical reactions. So when you drink ethanol and it gets you drunk, it's a different reaction than burning it in your car, which is a combustion reaction. But ethanol is organic substance, we call it. It has a dipole. Okay. If you remember what I said, is that if you have a substance that's made out of carbons and oxygens, the molecule would be polar. Typically, if the ratio if the ratio of carbons to oxygens is greater than 3-to-1. And that's not a law, that's just kind of a rule of thumb. And you can see here, ethanol has 2 carbons and 1 oxygen. And therefore, based on this rule of thumb, it's polar. And it has a negative and positive part, okay? And that negative and positive part has a dipole. And so this can interact with water, because water has a dipole as well. Okay, so ethanol can dissolve in water and form a solution. On the other hand, immiscible solutions are two liquids don't mix. For instance, like oil and water. And it has to do with polarity. Okay, again, if you have a nonpolar substance like benzene, okay, and again, there's sort of a rule of thumb. The ratio of carbons to oxygen is 6-to-0. Okay, so this would suggest I have a nonpolar molecule. And again, the reason why why these don't mix is that water's attracted itself, and benzene doesn't have any plus or minus for the water to interact. So these would separate. So you would get 2 phases. You'd get a water phase and then a benzene phase. Okay, and general rule of thumb is like dissolves like, and what we mean by that, polar substances dissolve polar substances. And the opposite is true as well. Nonpolars dissolve nonpolars. Okay, learning check. Which of the following are miscible? That means dissolves in water. Okay, so you have to know something about these. Okay, so acetic acid. It's good to know the chemical formula. It's C2H4 O2. Okay, and this will help you actually probably more than this, the structure. Remember I said is if there's carbon and oxygens, the ratio should be greater than 3 to 1 to be nonpolar. So you can see that this is a polar molecule. So it's going to dissolve in water. Okay, ammonia, NH3, okay. Again, if you look, you have to know, this structure is actually good to know, okay. It's missing something. It has missing the lone pairs. And remember is that if the structure has 2 or more things attached to the center atom, it's probably going to be polar. So ammonia has a nitrogen in the middle, and then it has hydrogens and lone pairs. There are 2 different things here. Hydrogen's a thing, and lone pairs are a thing. So this is a polar molecule as well. So it's miscible in water. And carbon disulfide, you can tell that this is polar or nonpolar. If you look at the shape, there's no lone pairs on the center atom. It has the same thing attached to the center atom. So this is going to be nonpolar. So this would be immiscible in water. So if you put carbon disulfide in water, it would not mix. Okay, now let's look at this one. Which of the following molecules is most soluble in hexane? Okay, first of all, determine if hexane is polar or nonpolar. All right, it's going to be nonpolar. And how can you tell? Kind of, you have to, it'd be nice to look at this structure and go through all the details of knowing polar and nonpolar in terms of bonds and stuff like that. But if a substance has a lot of carbons, it's usually nonpolar. So when we look at these 5 right here, the substances that are nonpolar will mix with it. Okay, so let's look at the options. Okay, from the last slide, we see that ammonia is polar. Okay, so we can apply nitrogen to the carbon-oxygen rule, okay? It's a little bit more stringent I said that if you had a ratio of 3, greater than 3 to 1 is nonpolar. Probably for a substance with nitrogen, it's probably a lower ratio. It's probably like 2 to 1, okay? It's probably 2 carbons for every 1 nitrogen would make it nonpolar. So if we look at here, we have a 1 to 1 ratio. So we could see that's less than this. So this is polar. Again, this is a rule of thumb. Now I don't know how good this is, but it's oxygen is more has higher electronegativity, so it would have bigger effect than nitrogen. So you might just want to keep this in mind. All right. Again, this kind of this rule over here. So this would also be polar. Okay. This is nonpolar. No oxygens or nitrogens, etc. And then we know that water is polar. So we know that this guy, which is ethane, is our pick. Okay. Now, let's see if you can figure this one. So I won't talk about it. See if you figure it out, and then I'll go over it in a second. So you might want to just turn this off and guess on your own. Okay, so let's go back and look. Now, is this polar or nonpolar? Well, one of the things I want to make sure you understand is that if you see, this is both polar and nonpolar, but it's more likely to be nonpolar, okay? It's not completely nonpolar. So if a substance has carbons and oxygens, carbons and nitrogen, they will be not both polar and nonpolar, but there'll be a tendency for one or the other based on kind of that rule of thumb I told you. So this is mostly nonpolar. Oh, let's go back to this. This is polar. because the ratio is less. But we can learn that, identify that, because the ratio is less than 3 to 1. So this is polar. So this might be slightly polar. Okay, so this might be slightly soluble. Okay, this one is probably more polar. Okay. All right, this one is even more polar because, the ratio has 3. So this has both polar and non-polar. So, but the ratio is 3 to 1. So it's kind of pushing on the non-polar side. Okay, so far this one's the most likely to be soluble. Okay, this one is insoluble, doesn't have any oxygen or nitrogens. So this is nonpolar. And then this one down here, look at the ratio. It has, there's 2 oxygens to 2 carbons, so the ratio is 1 to 1. So this is definitely polar. So this one here is going to be our pick. Okay. This would probably be our second best. And then either A or C, and then D. Hopefully that helps you out. I hope you're getting the idea of how this works. Okay, solutions of solids and liquids. So this is like when you put salt in the water. Basic principles remain the same. For instance, okay, you put sodium chloride in the water. The sodium has ionic bonding, so it has to break apart its ions before it can dissolve water. And it can form good interactions in water. So ions dissolve in water because the ion dipole forces the water with the ions strong enough to overcome the ion-ion attractions. Okay, first thing we're going to talk about is we could talk about hydration. And hydration is what happens with the sort of the salt, so like sodium, an ionic compound. When you put it in the presence of water, okay. And so an example of this hydration is, first of all, what is hydration? Hydration is what happens to the ionic compound when it's exposed to water. And this could mean one of at least two things. One is exposed to any amount of water, even a slight amount of water, and also being dissolved. So one way to think about the first one is, you may know is if you have some sodium chloride, maybe if you're in a salt shaker, or even if you have a bag of salt that you put out to help melt the ice, which we're going to be talking about soon, how that works, is if you leave it out, you'll notice is that the salt will all clump together. And why does that happen? Okay, and that's because the sodium chloride has been hydrated. And what happens is that the water and the air will start interacting with the outside atoms of the salt particles. And what they'll do is the negative part of the water, the water has the dipole, has positive part with the oxygens and negative part of the hydrogens, and negative part with the oxygen. That'll surround the sodium. Okay. In fact, it'll surround the sodium so much, if you allow it, is that this attraction here will actually be as strong as the attraction between the sodium chloride, and it'll break apart the sodium chloride. And the same thing happens with the chloride, where the positive part of water interacts with the negative part. Now, in this, so you will have a hydrated sodium chloride. Now this process also happens when you dissolve the sodium chloride in as well. So hydration versus solvation, ions surrounded by water molecules. So, and this is, so if you have copper sulfate is an ionic compound. Okay. All right, and so it has a sulfate and a copper. And if you, it's a white crystalline substance. But if you leave it out in the air, and air has water in it, okay, just a small degree, what happens is it will attract water molecules. And there will be 5 water molecules attached to every copper sulfate. And it does that in a very unique arrangement, okay? And then so we say that the copper sulfate has been hydrated, okay? So we're talking like these individual particles. And oh yeah, when you add the waters, it turns blue, which is cool. And if you want to unhydrate it, which is easy to do, you just add heat, and you will get unhydrated. Okay, solvation is where you take the ionic compound and you put it into a solvent. Okay, where for this case the ratio of the solvent to solute isn't that, it's not that great. But in this case, it's great. The amount of solvent to solute is great. And this is where we get dissolving. Okay, so this just shows you how it works, the positive, the negative, and so forth. But oh yeah, so this one is not sodium chloride. This may be like glucose. Glucose is a kind of sugar. Okay, it has chemical form as C6H12O6, and it's polar. You can kind of get that by looking at the chemical formula. So these little ovals in here are glucose. Okay, so when you put glucose in the water, what happens is the negative part of the oxygen is to interact with the positive part of the glucose. So glucose has a positive end and a negative end as well. And so when you put it in water, the water will the positive ions will interact with the positive part of water will interact, negative part of water will interact with the positive glucose, and so forth. So there's this would be a dipole interaction. When you put ionic compound into water, it's an ion dipole interaction. And we went over that in the last slides. Okay, solvation in nonpolar substances. Okay, wax is a mixture of long chain alkanes and is very nonpolar. Benzene is the nonpolar solvent, and benzene can dissolve waxes. Okay, how do they interact? Well, they don't have any dipoles. Okay, so what do? They form London dispersion forces. Okay, now, so why do they mix? Okay, the key thing about nonpolars is that the wax molecules, when you put them into the benzene, okay, what they do is they slide in. So here's the benzene molecules. And when you put the wax in it, what it's going to do is slide in between the particles. And when it does that, it's a long chain, has a lot of surface area, okay? And when it can just slide in here, it will interact and be able to be polarized and form London dispersion forces, okay? All right, so the main thing about when you mix nonpolar is you got to mix them, all right? And so you can maybe have to shake them up and whatever. But once you mix them together, they will form good interactions because they have to slide in and mix with each other. And when that happens, they can form these London dispersion forces. Okay, heat of solution. The heat of solution is what is how much energy is released or absorbed when solvent and solute are mixed. Okay, and the term is called molar enthalpy of solution. Now, I know I went over this in Chem 121. Is that you got to be careful about this word heat. Okay, remember what's happening here is, so when you have your solvent and then your solute to make your solution. Okay, what we're saying is that this side has a high enthalpy, and this side will have a lower enthalpy, and the difference between these two enthalpies will be some energy, which is a change in enthalpy. All right. Now, that change in enthalpy, that energy, okay, will manifest itself in the surroundings as heat. Okay, so what we could do is we can measure the heat in the surroundings, and we know that heat came from this energy. So this energy here, so there's not heat that's released. This is not heat. This is energy. And then the heat is energy is converted to a kind of energy called heat. So if we measure this heat, we know that that's the energy that was released, which is the difference between these two. Okay, so this change in enthalpy, okay, is equal. It's not the same. Is equal to the heat. Okay, and it's also equal to change. But it's also known as the difference. Okay, so delta can mean two things. It can mean change and different. Okay, so when you actually look at the chemical reaction, it has a change in enthalpy, which is equal to the difference, and it will manifest itself as heat. So when we say heat of solution, it relates to the enthalpy. Okay, and usually what we want to do is in terms of moles to be specific about a type of reaction. Okay, so heat of solutions, you can have it be could be endothermic or exothermic. Most of the time it will be exothermic. We'll talk about this. Both of these. In this case, what you're going to be noticing is it's just that the surroundings will be getting colder. Okay. An example of that is if you take ammonium nitrate and put it in water, the temperature will go down in the water. And so in this case, what happens is that your two guys, your solvent and solution, okay, when they go to solvent and solute, these guys will have a lower enthalpy than the solution, so it has to add energy. And the energy comes from the surroundings as heat. So heat is lost into the system, and then it increases the enthalpy to make the solution. And this one here is from the previous slide I just talked about. Okay, usually this will be the case, but you'll get this, and this particular case is less likely to happen, and usually requires us to think more about this thing called entropy, which we'll talk about later on. Okay, so let's actually try to model what happens in terms of energy when you form a solution. So we talked about this already. So when you have a solute and like a solid and a liquid, this here is solute and solvent. What happens? Well, there's two steps. The first step is to break apart the solute and solvent into particles, and that requires energy. Okay, so it's an endothermic reaction. Okay, so the enthalpy, this step, step one, okay, is a endothermic reaction. Okay, step two is usually, okay, it's when they come together and their intermolecular forces come together, is usually, well, is going to be, if they mix and form a solution, this could be exothermic. And then what you have to do is add these two together. And like I said from previous, if this term here outweighs this term, you'll make a solution. So let's be more specific about this and look at some examples. All right. Before we do that, let's kind of look at like Hess's rule. Remember, Hess's rule says it's a if you have, let's say you want to look at a reaction going A to C. Okay. Well, so you want to turn A into C. Well, you could just take A and then it'll turn into C. But another way you could do it possibly is you could have A turn into B, and then it has some certain amount of energy. Okay. So we'll say this is some enthalpy change here. And then you take B and you turn it into C, and it has its own enthalpy. And then when you add these two together, you end up A going to C, and then the sum of these two guys is the sum of this, which is what we just showed in the last slide. So you add your steps together, So in our case, the first step is to break apart the solvent, break apart the solution, and then just break apart the solvent, break apart the solution, which are both require energy. And then this should be solution, okay? And then the mixing. This should be the enthalpy of the formation of the parts, and that will equal the total solution. All right, so let's look at an enthalpy diagram of this. So the first step is to break what we're going to do is let's say we take salt and put it into water and dissolve it. Okay. So the first step is actually break apart the salt and the sodium and chloride in its individual particles. And so now the individual particles, the sodium chloride, kind of act like a gas. Okay, so that's going to require energy. So you have to break apart the lattice of the sodium chloride. So you have to add this much energy. Okay, so that's this right here. Okay, and you can see it requires 632 kilojoules per mole. Okay, and then the next thing you need to do is dissolve the gas in the solvent. Okay, we're skipping kind of. Well, this is sodium iodide. Sorry, I mean this is potassium iodide. So you're breaking the potassium iodide first into its parts, kind of like gas, and the next part is you put this in the water. All right. Okay, and when that happens, the plus parts interact with the negative parts of water, and negative ions positive water. What happens is that the entropy goes down. So the yeah, this is negative, all right? Now, then you form your solution. Now, one of the things you notice here is that this is an endothermic reaction. Typically, if there was nothing else involved with it, this would not dissolve, because what you would like to do is have this go further down. It should take less. This energy here to actually mix to form this interactions should outweigh this. Well, we're seeing that it doesn't. Okay, so this does form. So sodium iodide does dissolve in water, but the reason why it doesn't, I mean, why it forms even if it doesn't go under, okay, going further down, is because there's another factor which is entropy, which we're not going to talk about. So you can have you can form a solution that's endothermic. Okay, we know that it mixes. We know these two things happen. We know that this goes up, and you need to break them, and then we know that this goes down. Okay, but if there was nothing else concerned, these two would not dissolve, because this step doesn't outweigh this step. But we know this happens, so there must be something else involved. So right now, just don't worry about that. Okay, this is that there are two steps here. Okay, you have to break apart the lattice, and then you have to have the solvation. Okay. All right. So it's just another diagram of it. Okay, so this is one. This one is more related to that. So the first step here, let's say you have some sodium bromide, Na plus, Br minus, and it's a crystal. So the first thing you have to do is to break apart the crystal. So you have to add enough energy to break apart the lattice, and it's that amount. So add it up at that amount, 728, and then you put it in water and hydrates, and then it goes down this much. And so the difference between the two is negative 13 kilojoules per mole, and that's an exothermic reaction. And in this case, this does happen based on what we kind of would assume based on enthalpy. All right, so here's a little side question. So, of the following ions, which would have the most exothermic enthalpy of hydration? So what that means is which one would be the most likely to interact with water? Well, the one with the most charges. Okay, so gallium has 3+ charge, so it's going to interact with 3 times as much water. Okay, so gallium 3+. Okay, what we're going to do now is look at how we can actually determine the heat of solution. And this is going to be basically one step. This is going to be taking, it's not going to be looking at the two steps. It's just going to look at the overall change in enthalpy. It's not going to look at the lattice energy and the solvation energy. This is going to look at the overall effect of the heat of solution and how we can figure it out. Okay, and we're going to look at an exothermic reaction, The same thing could apply for endothermic reactions, how we figured out. So the idea is this: is if you have a solute, and it's a solid, and you put it in water, and then it becomes a solute that's been dissolved. And so we're leaving out the water component because we're just looking at what happens to solute. So the solute goes from a solid to aqueous. In a sense, kind of like a liquid. Okay, so it's kind of though it's not technically a liquid, it's a mixture. Kind of cool thing to think about this is that this is going solid to liquid in a sense. So this is kind of like chemical melting. All right, this is you're kind of going solid liquid. That's just a side thing to think about here. And it's solid to liquid, but it's aqueous actually. So you have your enthalpy. The solute's going to have a higher enthalpy, and this represents the circle here. So enthalpy of solute, and then you have your enthalpy of your solute. Solution. This would be solution. Yes, this is solution. AQ. Yes, and the difference is difference in these two energies is the change of energy that's given off, which we can measure. We'll show you how to figure that out. So what we do is we're going to do we're going to do this reaction in a closed system. Now remember, there's three kinds of systems. There's something called isolated system, where the energy of this, so you have your surroundings out here, and then you have your system. For a closed system, what happens is energy can move in and out, and matter can't. Okay, so all the matter stays inside. Now, if it was an open system, energy and matter would move between the system surrounding. An isolated system is where all the energy and the matter stays within the system. So what we're going to do is close the system off to moving matter, but only allowing energy. So what's going to happen is so this guy's going to have its initial enthalpy, and this guy's going to have its enthalpy. And then the reaction takes place, and then it gives off energy. And that energy is in the system, and when it goes to the surroundings, it's turned into heat. Okay, if we can measure how much heat is given off, we know that that's equal to the amount of the change of energy, which is the difference in of energy. So this heat here, okay, is going to equal, but with opposite, okay. So if this heat goes up, this enthalpy, so the enthalpy has to give it off. So, right. So they're not equal. Remember, equal here is a comparative. It's not the same thing. We're not saying this is the same as this. We're saying if I know this, I know this. So that's what we're going to look at here. So the change in temperature of the surroundings and the heat added to the surroundings are related according to the formula. So if I know the change in temperature of the surroundings, that has to be due partly to the change in heat of the surroundings. So if you add heat to the surroundings, the temperature is going to go up, and we can use this formula. M stands for the mass of the surroundings. C is the heat capacity. Okay, so I just said over here that this enthalpy change or difference is equal but opposite to the heat that's given off or absorbed. And then what we can do is we can replace this with this over here, and then we get this formula. So what we can do is we can measure this on the surroundings, And then we know, since we know these two are equivalent, okay, we can figure out this. And that's what we're going to do. Show an example of that. Okay, so your turn. So what the idea is, I'm going to take 2.5 grams of solid sodium hydroxide, and I put it in 100 grams of water and put it in a calorimeter. A calorimeter is a way of measuring the heat that's given is a way of measuring temperature. And again, you can measure the temp. If you know the temperature, you can know the heat. And when we do this, the temperature of the calorimeter increases by 6.5 degrees Celsius. And what I want to do is I want to find out what is the molar enthalpy of solution. So how much energy, what is the change in enthalpy per mole of sodium hydroxide. Okay, and we're going to need this right here because this is the heat capacity. So let's see how we do that. All right, so here's our formula from previous slide. It should be a delta. Okay, so the heat of solution. So the mass of the solution is the mass of the water plus the mass of the sodium hydroxide times the heat capacity times change temperature. And we should really put a plus sign in front of this. And remember, there's a negative sign here. And when we do that, we come up with negative 2,788 joules. Okay, now what we're saying is that that's how much heat is released when you put 2.5 grams of sodium chloride in water. So it's very specific. It's specific for 2.5 grams. What we want to do is not have this in grams. We want to know how many moles this is. So we just figure out the mass moles of sodium. So you divide that by the molar mass of sodium hydroxide, and you get this many moles. So it's negative 2,788 joules, negative per 0.0625 moles of sodium hydroxide. Okay, how about sig figs? This has 3, this has 4, this has 3, so your answer can only have 3. So your final answer will be negative 44.6 kilojoules per mole of sodium hydroxide. And so what that means is that you have sodium hydroxide, which is a solid. Okay, and then it goes to an aqueous solution. Okay, and the enthalpy change per mole is going to be this amount here. So this guy here had more enthalpy than this guy by this amount. Okay, so now let's look at what happens when you add liquid solute. Okay, I talked about this earlier with ethanol. Like when you put ethanol in the water, the ethanol dissolves. Okay, there's 3 steps here. So the first thing is the solute has to be expanded into gas. So if this is ethanol, first of all, you have to have it break apart and behave like a gas. And this again requires energy. All right. Okay. The second thing to do is you got to have the solute do the same thing. Okay, and that's also going to be endothermic. And then the mixing of two with the intermolecular interactions will be solvation, and they'll mix together, and that be delta H is negative. So these first two are going to be positive and then negative. So when you add these 3 together, there's 3 parts. For the first 2 are positive enthalpies, and the third one is negative. And then when you add them all together, that's going to be the overall um, heat of solution. Okay, there you go. Okay, now let's talk about gases. So gases can dissolve in liquids as well. For instance, um, when you make your carbonated drinks, what you do is take carbon dioxide and then you put it into water and it dissolves to a certain degree, and you can actually increase or decrease the how well the carbon dioxide dissolves in water based on temperature and pressure, which we're going to talk about in the next slide. Um, so only very weak attraction exists between gas molecules. So that's key thing. So remember, gas molecules basically are not attracted, and that's one reason why they're gases. So when making a solution with gas solute, you don't have to break apart the gases. So you don't have to do that first step to break apart. Like in the solids and liquids, you needed first to break them into the quote-unquote gas particles. And then when you mix the two together, you have then what has to happen is the solvent has to expand a little bit to have the gas molecules fit into it. And then if there's attractions, we'll have this would go down, this would go up, and then if it's overwhelmingly, you'll get a solution. All right, so let's kind of look at what happens here. So the first step, the gas dissolves in organic solvent, generally endothermic reaction. Dissolves in water, exothermic reactions. Okay, so anyways, what happened here is if you have gas and an organic solvent, maybe like gasoline, what's going to happen is that first of all, you have to expand the organic solvent. Okay, so and then the gas particles can go in there and fit. Okay, now what happens is that then this step here, the actual interactions between the gas particle and an organic solution solvent usually aren't all that great. Okay, they're just held together by dispersion forces, and so the enthalpy doesn't go down a whole lot. Right, versus something like water, which is polar. First thing again, you have to get the water to separate. Then you put which is that endothermic part. Then you fit the gas particles into it, and usually the reason why these gas particles fit in here and stay in there is because they form dipoles, and that's a much stronger interaction. Okay. All right, so that ends this first slide, and in the next slide there's going to be more specific examples and more calculations on using how mixtures are made.